Welcome back to Future Mind GenAI Data Science podcast. I am your host Manav, and it's fantastic to have you join me for our sixth episode. In our previous episodes, we have covered broad spectrum of topics from the basics of neural networks to advanced reinforcement learning. Today we are going to explore vital area in the field of AI that is crucial for understanding and improving our models. Model evaluation and validation. This topic is essential for ensuring that our AI systems are reliable, accurate, and perform well in real world scenarios. Let's dive in. When developing machine learning models, it's not enough to just train them and assume they will perform well. We need robust method to evaluate and validate our model to ensure they meet our expectations and generalize well to new and unseen data. This process involves several steps and techniques which we will discuss in detail today. First, let's talk about importance of having separate validation set. When we train a model, we usually split the data set into three parts: training set, validation set, and the test set. The training set is used for training the model, and the validation set is used to tune the model's hyperparameters and evaluate the performance during development. And test set is used to assess the model final performance after training is complete. One common mistake is to use test set for tuning the model, which can lead to overfitting. Overfitting occurs when the model learns noise and details of the training data to the extent that it performs well on training data but poorly on the new data. By having separate validation set, we can mitigate overfitting, ensuring that our model is evaluated on data it has not seen before during training. Cross validation is powerful technique for model validation. In K-fold cross validation, we divide data set into K subset or folds. We train the model K times, each time using K1 fold for training and remaining fold for validation. This way, each fold serves as the validation set once, and the model is trained on different subset of the data. The result from each fold are averaged to obtain more robust estimate of the model performance, and this technique helps to reduce variance and provide more reliable evaluation. Now let's discuss evaluation matrix. Depending on the type of problem we are solving, classification, regression, or clustering, we need a different matrix to assess the model performance. For classification problem, common metrics including accuracy, precision, recall, F1 score, and the area under ROC curve. Accuracy measures the proportion of correct prediction, but it can be misleading in case of imbalanced dataset. Precision and recall provide more insight by measuring proportions of true positive predictions. The ability to identify all relevant instances respectively. The F1 score combines precision and recall into single matrix, offering balance between two. For regression problems, metrics like mean absolute error, mean square error, and R square are commonly used. Mean absolute error measures the average absolute difference between predicted and actual values, and mean square error these differences, giving more weightage to large error. R square indicate the proportion of variation in target variable by the model. Another crucial aspect of model evaluation is the confusion matrix. Especially in classification tasks, a confusion matrix provides detailed breakdown of model predictions showing the count of true positive, true negative, false positive, and false negative. The matrix helps in understanding the type of error the model is making and provide insights for further improvement. Let's discuss the concept of bias variance trade-off. Bias refers to error due to overly simplistic model that fails to capture underlying pattern in the data, leading the underfitting. Variance refers to error due to overly complex model captures the noise in the training data, leading to overfitting. The goal is to find the balance between bias and variance, achieving model that generalize well to new data. Techniques like regularization, which we'll discuss in further episode, can help in managing this trade-off. Another important aspect of handling imbalanced data set in many real world scenarios we encounter data set where certain classes are significantly underrepresented and compared to others. For instance, in fraud detection, fraudulent transactions are rare compared to legitimate ones. In such cases, using accuracy such as Sol matrix can be misleading. Techniques like resampling, synthetic data generation, and using different evaluation metrics like precision recall curves can help in effectively handling imbalanced dataset. As AI systems are increasingly being deployed in critical application, understanding how they make decisions become essential. Model interpretability refers to the ability to understand, explain the model's behavior and prediction. Simple models like linear regression, decision trees are inherently interpretable. But more complex models like deep neural networks are often seen as black boxes. Techniques like LIME, local interpretable model, agnostic explanation, and SHAP, shapely additive explanations, provide insights into model prediction by approximating contribution of each features in the final decision. This helps in building trust, ensuring transparency in AI system. Let's discuss the example of illustrate importance of model evaluation. Imagine you are developing model to predict loan defaults. You have data set in various features like income, credit score, employment history. You split data set into training, validation and test sets. After training your model, you evaluate its performance using accuracy and it achieves 95% accuracy. Seems impressive, but upon closer inspection, you notice that 5% of loans in your dataset are default. This means your model could simply predicting every loan as non-default still achieve 95% accuracy, which is not useful in practice. By using additional metrics like precision, recall, and confusion matrix, you can get a clearer picture of model performance. You might find that your model has high recall but low precision, indicating that it's predicting most default correctly but also labeling many non-default as default. This insight can guide you to adjust your model, perhaps by using techniques to handle imbalanced data by tuning its threshold for classification. Lastly, let's touch upon ethical considerations in model evaluation. Ensuring fairness and avoiding biases in AI models is crucial, especially when these models impact people's lives, such as hiring, lending, and law enforcement. Bias in training data can lead to biased model, which can perpetuate even amplify existing inequalities. It's important to evaluate models for fairness by examining their performance across different demographic groups, taking steps to mitigate any bias found. This includes using techniques like fairness aware algorithm and ensuring diverse, and representative training data. Thank you for joining me today for Future Mind podcast. I hope you find this uh, podcast helpful. Make sure to subscribe so you don't miss any upcoming episodes where we will continue to explore incredible potential of generative AI and data science. Until next time, I am your host Manav signing off. Stay curious, stay inspired, keep exploring. Thank you.